All right, well, I will begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. I thank you for the nice weather outside and for these students. Just ask that you be glorified in what we do. Help us to understand the math we're going over, and just for the students to ask any questions that arise. Lord, in your name I pray. Amen. Okay, so I guess this is lecture 17 by my count. So the top hat code is 2939. All right. So we're talking about different number systems, and so let me just kind of be a little bit more, if you don't mind, let me be a little bit more formal here, if you will, in terms of what we mean by base. Let's say base A. So if I have a number like, you know, let's see here. I'm going to write it this way: n0, n1, n2, dot, 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 nk. All right, and that number is base A. All right, what that means. All right, so the number, so the leading digit is n sub k, and then I've got n dot 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 dot, n sub 2, n sub 1, n sub 0 here. If that's the situation, what that's equal to is n sub k times a to the power k plus, and so forth and so on, all the way down to n sub 2 times a to the 2 plus n sub 1 times a to the 1 plus n sub 0. Right, times a to the 0, but a to the 0 is 1, so we don't really need to write that. So like, this is a representation of a number in another base, all right? So we're most usually thinking about this as base 10, right? So like, our default way of thinking about numbers, the way we've, I think, pretty much all been raised, is, because I don't think any of us here are like Babylonians or anything like that, and the Mayans are kind of gone. So, but here's an example, right? 374 is equal to 3 times 10 squared plus 7 times 10 to the first plus 4, right? So that would be base A equals to 10. So our convention is, in base 10, we don't force ourselves to write the sub A like that, right? We just say it's base 10. Okay, that's a Hindu Arabic number, which I would just say is, you know, a regular number. Another example here would be something like 1, 6, 7, 0, 5, and let's say, and for reasons that I don't entirely understand, we insist on writing out the word that is the number for the base in your textbook. I think it's mostly they're putting this, like they're writing, I think your textbook writes out the base like this just to really like grab your attention and go, hey, something weird's going on here. So they just write out the number 8 like that. I've really never seen that anywhere except for your textbook, but fine, it's nice. So if we're dealing with powers of 8, if you count here, this is, so the ones digit is the 0 power, 0, 1, 2, 3, 4. 4 is my highest power, so I do 1 times 8 to the 4th power plus 6 times 8 to the 3rd power plus 7 times 8 squared plus 0 times 8 to the 1st power, and then plus 5. This is base 8. Base 8. This is also known as an octal number. All right? In the world of computer programming, And suppose you're working for a business and you get a computer file and you're a programmer, or you're looking for work, so you took a programming job. You don't really know what you're doing, but here you are, you're doing it, right? And you get this computer file and you look through outputs and stuff and you see the number 16705, right? The question then you have to ask yourself as a computer programmer is 16705, is it a regular base 10 number? Or is it a base 8 number? See, because it could be either. And I'm not just being hypothetical. Like, I worked for the Navy for a year, and one of the annoying things is you get data sometimes in octal. And if you look at a page of numbers and there's no 9 anywhere to be seen, and there's no 8 anywhere to be seen, it's like, maybe this is octal, right? See, there's the difference. In base 10, and my example fails to show this, right? But here, let me fix my example. Instead of doing 374, let's do 974. That's easy to change in my font. Check it out, you. Hey, I can say that. It's part of my life experience. No snickering. So 9 is a digit which is available to base 10, right? But 9 is not something you can put in an octal number as a digit. So what are the terms and conditions for the digits here? I haven't told you yet. What these n1s, this n1 through n0 at the start, where do these have to be taken from, right? We have 0 less than or equal to n sub I, less than or equal to k minus 1. Right? So those are your digits. So like a base 10 digit can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We're used to this, right? Octal digit can be 0, 1, 2, 3, 4, 5, 6, 7, but it can't go past 7. That's the rule. All right? Let's look at another one here. We could have 1, 0, 1, 1, 0, 1, 1. That is a binary number. What would that mean? So this would be, let's see here. Let me count. So here's the ones place. So 0, I start counting at 0. 0, 1, 2, 3, 4, 5, 6. That first 1 represents a 2 to the power 6. So we have 1 times 2 to the 6th plus 0 times 2 to the 5th plus 1 times 2 to the 4th plus 1 times 2 to the 3rd plus 0 times 2 to the square plus 1 times 2 to the 1 plus 1. This is base 2. Such a number is called a binary number. All right? And of course, we can get out our calculator and find the values of each one of these numbers base 10, right? Like, well, 974 base 10 is 974, right? That's done. What is the 16705 base 8? Did anybody calculate it for me? It's gonna make me do all the work. All right, fine. So 8 to the 4th plus 6 times 8 cubed plus 7 times 64 plus 5. I get 7,621 in the usual number system, right? So this guy is equal to 7,621, right? Now, how about that binary number right below it? What's the value of that in base 10? Let's see here. So we just have to add those numbers up, right? I don't think I need a calculator for that one. 2 to the 6th is what? Well, 2 to the 6th is 64, I think. So you got 64 plus 0 plus 16 plus 8 plus 2 plus 1. That is equal to 80, 88, 90, 91. Right? So this, of course, is the base 10, right? Representation of that binary number. So any number, any integer, any whole number, if you will, we can either choose to represent it as like a base 10 number or as one of these other bases if you want, right? And so what we're studying at the moment is like how to convert from one to the other. And I'm trying to be friendly to you guys, so I thought about doing arithmetic in these other bases, but then I thought, let's not. So, because I don't know, I can't get past the idea of like adding in other bases. To me, the book has how to do it, right? And maybe that's interesting, but I don't think it's worthwhile for us to do in here. I'm just going to focus on the issue of how we go back and forth from one number system to the other, all right? So there is material in this chapter which I'm not testing you on. You can kind of tell in the homework what matters most, yep.
Why did you seem to be trying to convert the binary number to base 2, but then you were base 10?
Well, it's given in base 2.
Okay.
And this, like this expression right here, it's, well, I mean, this is a base 10 numbers. What I've written on the right-hand side, these are all base 10 numbers. So the same number, all right, can be represented in base 10 as 91, but it can be represented in base 2 as this. And the Egyptian hieroglyphics, what's 91? Remember last time? So in terms of Egyptian hieroglyphics, it would be like heel bone, heel bone, heel bone, heel bone, heel bone, heel bone, heel bone. 1, 2, 3, 4, 5, 6, 7. Heel bone, 8. Heel bone. What was the thing? Stroke? There you go. There's the annoying Egyptian hieroglyphic form of this thing. All right. And what would it be in Roman numerals? I need 90 plus 1, right? So I do take away 10 from 100, so I do x, c, that's 90, and then 1. So there's Roman numerals. These are all the same number, right? This and this and this and that, they're the same number, but these are different representations of the number is the idea. Can I go on? So there's something. Part of the reason I admit my reasons for covering this material in part is because I wanted to do this. It looks stupid, and I just wanted to try it out. So let's try it out. 1 0 1 1 0 1 1. We just did that one, yeah. And so the book says. Let me stretch that out a little bit. It's got this double double method. Double double. Double double. So let's try this double double thing. So I'm gonna try out the double double. Now I just read about it, so let's see if I can do it right. And if I do it right, great. If I don't, then I'm gonna have to get the book out and fix it. So let's hope it works right the first time. I believe you start with the number 1. All right? And if the next number you go to is 0, you double it. So 1 goes to 2. So that's a double. If the next number you go to is 1, you dabble. What's dabble? Dabble to the book means you double the number that you have and add 1. So to dabble 2 is to do 2 times 2 plus 1. 2 times 2 plus 1 is 5. So 2 times 2 plus 1 equals 5. They dabbled. And then we dabble again. Dabble. It's exceedingly silly. So 5 times 2, or let me say it this way, 2 times 5, sorry, 2 times 5 plus 1, that would be 11, right? Now I got 0, so I don't dabble, I double. Double. So double 11 times double 11, you get 22, right? And then I go to 1 again, so I dabble. So dabble 22, 2 times 22 plus 1 is what? 44 plus 1 is 45, yeah? See that? And then I dabble again, right? And 45 times 2 is, so I do 2 times 45 plus 1, what does that get me? What did we have? Isn't this stupid? So this is the double dabble method for calculating a binary number. Want to try it on another one? Let's try it on something smaller. Let me do all dabbles all the way down. Dabble, 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 dabble. 1, 1, 1, 1. All right. So I start with 1. I double it, and I add 1, right? So 1 times 2 plus 1 is 3. Then I dabble again. 3 times 3 is what? Is 9. Excuse me, 3 times 2 is 6. 6 plus 1 is 7, right? So 2 times 1 plus 1 is 3. 2 times 3 plus 1 is 7. And then dabble again. 2 times 7 plus 1 is 14 plus 1 is 15.
Professor, 2 times 1 is not 3.
2 times 1 plus 1 is 3. If I said 2 times 1 is 3, that would, of course, be nonsense, even for me. Let's see here. So dabble, dabble, 3 dabbles, right? Dabble, dabble, dabble. 3 dabbles gets me to the fact that 1, 1, 1 base 2 is equal to what? By this method, it's equal to 15. All right? So I don't know. This is actually a pretty fast way to calculate the value of binary numbers using this method. So I think I recommend it. It's not that hard to implement once you get used to it a little bit. It's pretty fast. Let's see here. So that was 2. Now, I should talk a little bit more about, we talked about binary, I've talked a little bit about octal. There's also something called hexadecimal, which requires discussion. So let's talk about that. What's hexadecimal? So hexadecimal is A equals to 16. A equals to 16. You need digits that go from 1 to 16. Now, in your textbook, they talk about the Babylonian numbers, right? What the Babylonian numbers look like? I'm going to let you read about it. I'm not going to really present that in class. I don't think I even assigned any homework on it. I could be wrong about that, but it's not hard. But like the Babylonian numbers are based on these. Oh, come on, where'd you go? Really kind of funky looking digits. Come on. I'll find it eventually, guys. The hexadecimal number system is introduced on page 323 of your textbook for what it's worth. Rats. Where on earth is that Babylonian number system? Sorry, guys. I just flipped past it somehow. I think it's in section 2. It's got these little like wedges. Oh, here it is. Oh, I'm not thinking. I'm thinking of the Mayan number system. I think the Mayan number system's got. Oh, here it is. Here it is. I said Babylonian, but I meant Mayan. Here's like Mayan numbers. Check this out, right? So the Mayan numerals. I think I've given you guys a homework problem on Mayan numerals, but let me just tell you in advance, I would not test on the Mayan. Like Mayan numerals will not be on the final or the next test. I think it's too weird. So I'll let you work the homework problem on it, but that's kind of as far as it's going to go, okay? With the Mayan numerals. But the Mayan numerals are very weird in that 0 is this like, is that an I? Maybe it's an I, I don't know. The number 1 for the Mayan numerals is a dot. The number 2 is 2 dots. The number 3 is 3 dots. The number 4 is 4 dots. 5 is a line. 6 is a line with a dot over it. 7 is the line with 2 dots. 8 is the line with 3 dots. 9 is the line with 4 dots. 10 is 2 lines. 11 is 2 lines with a dot. And it goes on, right? Up till 19 is 3 lines with a dot, 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 dot. And then they also use placeholders, but their base. So our bases, like the base I started with here, it's based on like a number. A to the 1 power, A to the 2 power, A to the 3 power. The Mayans used a different number for different parts of the placeholders. It's really weird. Like, let's see if I can find its next page maybe. Oh man. Sorry, I've lost the Mayans. Hey. Sorry. My standards for comedy are based on being a dad. So, say what you will. Anyway, I'm just the Mayan numerals are really weird. If I'd realized how weird they were, I wouldn't have put that homework in the. There's one homework on Mayan numbers, I believe. If I could delete it, I would, but I think some of you have already worked it, so I won't. Hexadecimal. The digits for hexadecimal, what are they? So this is where it gets weird. Well, it doesn't start out weird because you've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So far, so yeah, those are digits, right? And then this happens. A, B, C, D, E, and F. Those are the hexadecimal digits. So the way this works, just to give you I should have made a table for planning on my part. So here's your base 10. Here's your hexadecimal. So we've got our 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F. All right. I'm going to add a third thing here, binary. So hexadecimal 0 is base 10, 0, which is, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. But here, base 10, of course, that's 10. This is 11. This is 12. This is 13. This is 14. This is 15. All right? So A is equal to 10. B is equal to 11. All right? And C is equal to 12. D is equal to 13. E is equal to 14. F is equal to 15. All right? So I think it's interesting to actually look at the binary numbers here too. What are the binary? And so if you don't mind, I'm gonna be a little bit weird in my presentation of the binary numbers, in the sense that I'm going to write zeros that I don't need to write really. But I'm going to do that to make the pattern more symmetrical, okay? And so here's how that goes. Let me do it in red. So 0, well, first of all, let me tell you where we know where we're going, right? What was f? We just worked it out the previous slide. F in binary is by double, double, double. It was 1, 1, 1, 1. 1, 1, 1, 1 was f. That's f. And, well, 0 is 0, 0, 0, 0. 1, 0, 0, 0, 1. 2 is 0, 0, 1, 0. 3 is 0, 0, 1, 1. 4 is 0, 1, 0, 0. 5 is 0, 1, 0, 1. 6 is 0, 1, 1, 0. 7 is 0, 1, 1, 1. I'll stop right there for a second. So these are the binary numbers 0 through 7. Notice that there's 0 in like the leading digit there. That leading digit corresponds to power what? So we've got 0, 1, 2, 3. To put a 1 in this spot in the binary number is to say that you've got an 8 in your number, right? Well, we can't fit an 8 in any of the numbers up to 7, right? But once we get to 8, how many 8s are there in 8? Well, there's 1. So we go 1, 0, 0, 0. So that's 8. 8 plus 1 is 9. 8 plus 2 is 10. 8 plus 3 is 11. 8 plus, oops, my bad. That's 1, 0, 0. I'll have to come back and fix that. 1, 1, 0, 1. And finally, 1, 1, 1, 0. So those are your binary numbers. There's something really, really cool that happens with binary numbers and octal numbers and hexadecimal numbers in terms of like how they interrelate. So let me show you how that goes, all right? Example, I guess I'm example 3 in my numbering. All right, so here's example 3. So let's suppose we had, I don't know, 37 in base 8. What would that mean? That would be what? That means what? 3 times 8, right? Plus 7. So 37 base 8 is actually the number 24 plus 7, which is 31 base 10, right? 37 base 8 is 31 base 10. So let me do something. Let me take this 3 and the 7, and let me take the 3, and let me expand 3 as a binary number. So 3 becomes what? It becomes 0, 1, 1, right? 7 as a binary number becomes 1, 1, 1. So you can just look at the first, like ignore the 0 here, and that gives you the binary representations of like 0 through 7. Oh, by the way, I think this would be a wise thing to put on your formula sheet, because there's likely to be problems about like, binary numbers, and having this as a reference is like super helpful. Something like this. So what I'm doing is I'm replacing 3 and 7, base 8, with this number, base 2. So my question to you is, what is the value of 0, 1, 1, 1, 1? So can we figure it out? 0, 1, 1, 1. How many ones? 1, 2, 3, 4, 5. 5 ones, right? So if we wanted to calculate the value of that binary number, we could do what? We could use the double-double method to calculate it, right? So, I mean, your choice. Do you want to calculate this number double-double? Or do you want to calculate it from base principles?
Double-double.
Double-double it is. So double-double, we'll basically ignore the 0 at the front, right? Ignore that 0. Start at 1. So we start at the 1. And let me write it out a little bit better. It helps me to, I've got 5 ones, right? So my point here is that it's going to be what? Dabble, 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 dabble. 4 dabbles, right? So I go 2 times 1 plus 1, which is 3. Then I do 2 times 3 plus 1, which is 7. 2 times 7 plus 1, which is 15. 2 times 15 plus 1, which is 31. So therefore, by double-double, 4 dabbles, we get that 0, 1, 1, 1, 1, 1 base 2 is equal to 31. Hey, that's kind of neat, right? Because so what this means is that if you want to take an octal number and convert it to binary, all you have to do is take each octal digit and expand it as a corresponding binary digit and string them together. That's a pretty neat shortcut, isn't it? I think it is. And this is not an accident. This always works. So let me show you another example. And I'll do the example. Come on. So example 4. Let me zoom out a bit. Example 4, we might have like, let's see here, 4, 5, 0, 3, base 8. So this octal number, we can use the method that I just talked about, all right? And we can expand each octal digit as a corresponding binary triple. So like 4 is 1, 0, 0. 5 is 1, 0, 1. 0 is 0, 0, 0. And 3 is 0, 1, 1. And so that is the number base 2. Let me just rewrite the number. So like this is coming from the 4. This is coming from 5. 0 is coming from 0. And the 3 is this guy. So let me just give us a quick number here. 0, 1, 2, 3, 4, 5, 6, 7. And here's the binary. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So there's your quick rundown of the binary equivalents of the octal digits, 0 through 7. So I'm just using that, which I happen to have these memorized, but that's not because I'm a mathematician. It's because I started in electronics for 2 years, and I have a 2-year degree in electronics from Mayland Community College in Spruce Pine, North Carolina. And we had a course in digital logic design in there, and when you study digital electronics, it's all ones and zeros, and so you do a lot of stuff in like base 2, and you get familiar with these numbers, In fact, another thing you could use this for that might actually help you on the final is in terms of true and false. You can think of the 0 as false and the 1 as true. And this is the pattern for the truth table. If you look at it, it's like false, 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 true, false, true, false, false, true, 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 false, false, true, false, true, 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 false, true, true, true. those are the 8 logical possibilities if you've got 3 true or false variables. Now, that's not all that you can do here. All right, there's also, you can do the same trick for like hexadecimal numbers. Check this out. So if I've got, let's say 9 A B F, right? So that's base 16. This writing out 16 like this, it's really something to me. I'm going to regret leaving myself not enough space here, so I'm going to put it down here, okay? So what is 9? So 9, if you go back to my previous slide over here, see I go down here, 9 is 1001. So that 9 is 1001. My A is 10, which is 1010. My B is 11, which is 1011. My F, as we've talked about before today, is 1111. And so there you go. That's this hexadecimal number expanded base 2. I experienced this trick first as a wager in my community college. The professor bet that he could convert the hexadecimal number to binary faster than we could. And I think he bet us like $100 or something. So I'm sitting there with my calculator, and he gives us whatever number. I mean, it was relatively small. And I'm doing it, and he just spits it out, and I'm just like, what? See, because this trick is like stupidly fast. Once you have the hexadecimal binary table on the last page internalized, that's it. Now, what is this number base 10, by the way? Can you convert? Can you tell me? What would this number base 10 be? So my question to you is, how do you want to calculate this number base 10? I see 2 options. We could double dabble it. So it would be dabble. No, excuse me. It would be, how would it go? It would be like double, double, dabble, dabble, double, dabble, double, dabble, double, dabble, 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 dabble. I don't want to do that. It's too much double dabbling. I think the easier way to do this is just to fall back on what's the definition of hexadecimal to convert, right? So what's the base 10? What's this number? Base 10. So let's go back, let's do it. Sorry, I forgot to number my page over here. So base 10, let's try it this way. So we've got 9 A B F base 16. So this would be 9 times what? What does that 9 mean? F is the ones column, so we've got 0, 1, 2, 3. That 9 represents 9 times 16 to the 3rd power in your number. All right? And then you've got A. What is A? Remember, A is equal to 10. So 10 times 16 squared. What's B? B is 11. So 11 times 16. And then F? F is 15. So there you go. We just have to calculate those numbers. I mean, it's big, but you can do it, right? Now, I will say that some of you probably do have calculators that have conversion buttons. Like you might well have a button on your calculator to convert from base 10 to hexadecimal or things like that. I really don't know. I mean, I used to have a calculator that did that kind of thing, but it died a while ago. Whoa. Whoa. So yeah, that number 167809215. Put some commas in here. So 167,809,215. Yeah, there you go. So apparently you can do a lot with base 16, right? See that? What's the biggest number you can get with decimal? If we use base 10, like what's the biggest number you can get with 4 digits? What? 9999, right? 9,999 would be our biggest number in base 10, right? What's the biggest number you could get base 16? FFFF. How big is that? I'm curious. 16. That's as big as you can do with 4 digits. What would that be? That's 15 times 16. Now I'm just wasting our time, but you'll forgive me. Allow me the curiosity. 15 times 16 to the squared plus 15 times 16 plus 15. So that is 65,500 and what? Hey. How'd that happen? Hold on a second. Well, something is something not right here. How is it that my biggest number is 65,535 and yet I got 167,809,215? I do believe I made a calculator mistake right here. Let's try that again. 9 times 16 to the third plus 10 times 16 squared plus 11 times 16 plus 15 equals, oh, hey, that, shoo, goodness, I was like, I thought that number is huge. I guess I should have listened to my spider sense. Let's see here, 615. Although I'm not Spider-Man. If anything, I'm Batman. So I can prove it. Would you like me to prove it?
Yes.
All right, it's going to take a minute. Let me see if I have time. I'm not sure I have time to prove that I'm Batman today. We'll do it at the end of class, if there's still time. Okay, so one more example here. So up till now, I've done all the examples I've done so far, I've just been trying to make sure that we're all on the same page about what the number systems mean and how to convert from a non-standard number system back to base 10, right? But the inverse question of how to take a base 10 number and convert it to the other bases is more challenging, right? We did some of those last time, but we should do another, and we should talk about this. So example 6, let's take, let me call it n, equal to 10,378, all right? And let's talk about how to convert that to base something. What base do you guys want to do?
2.
Base 2. Okay, base 2 it is. I did ask for you guys. So let's find it in binary. So really the question is, what's the biggest power of 2 you can fit into that? Okay? So to ease my suffering, I'm going to start with 2 to the 10th is what? What is 2 to the 10th? 1,024, right? And then 2 to the 11th is what? 2048. 2 to the 12th? 4,096. I guess I could have calculated it in my head. And then you double that. 2 to the 13th is what? 8,196. Right? Let me check it before I do something foolish. Oops, see, I did something foolish. Wait, what? That was 96. I wrote 8, didn't I? 92. And then that's the biggest power of 2 we're going to be able to fit into this number. Agree? So this is biggest power of 2 that fits. So then what I do, well, I'm starting to really regret this example, but oh well, it is what I did. It is what it is. I did it. So 10,378 is equal to 8,192, right? Plus what?
Did you say 8,292?
No, 192. 8,001. 2 to the 13th is 8,192. So if I subtract 10,378, I get plus 2,186. Okay. And then how many? 2,186 is what? 2,186. I can fit a 2 to the 11th in that, right? So plus 2,048. Plus what? So what I'm going to do is I'm going to take 2186 and I'm going to subtract 2048 from that. That gives me 138. So what I'm trying to do is systematically peel off the largest power of 2 I can fit into the number. And I'm going to be able to write any number as a sum of powers of 2 like this. All right, so like 138, what can I fit into that? So if we had your formula sheet from like one of the previous tests, we'd be better, right? So we got, what do we got? 2 squared is 4, 2 cubed is what? 8. 2 to the 4th is 16, 2 to the 5th power is 32, 2 to the 6th power is 64, 2 to the 7th power is 128. All right, so we can fit a 128 into that, right? We can fit a 128 into a 138. I know we can do that. 8192 plus 2048 plus 128 plus 10, right? So let me do some color coding in my slide here. Let me show what's going on. This term right here is becoming both of these terms, right? And then this term right here is these two terms, right? So each time I'm taking the smallest piece and I'm chopping it further. And then finally, let me collect my thoughts here. So 8,192 was actually 2 to the 13th power. We have 2 to the 13th power plus 2048 was actually, what was it? It was 2 to the 11th power. All right, 128 is actually what? 2 to the, what was it? 7th power. 10 is 8 plus 2, right? Which is 2 cubed plus 2 to the 1st power, right? That 10 is equal to 8 plus 2, which is 2 cubed plus 2 to the 1st power, right? You guys see that? Now, what's the binary number here? I'll put some parentheses just to try to keep myself honest here. So 2. How many 0 digits do I have? None. All right, it's an even number, so we start with 0 binary. Then we got 1 of the 1st power. This is troublesome. I'm having to think too much here. Let me write more. Let me write more. So you have 1 times 2 to the 13th plus 0 times 2 to the 11th. 2 to the 12th, right? Plus 1 times 2 to the 11th plus 0 times 2 to the 10th. This marker's too fat. 0 times 2 to the 9th plus 0 times 2 to the 8th plus 1 times 2 to the 7th. Why did I let you guys talk me into this? Plus 0 times 2 to the, oh, that's right, I let you. 2 to the 6th plus 0 times 2 to the 5th plus 0 times 2 to the 4th plus 1 times 2 cubed plus 0 times 2 squared plus 1 times 2 to the 1st power plus 0 times 2 to the 0 power. And that is why this number in binary is 1 0 1 0 0 0 1 0 0 0 1 0 1 0 2. Can we work a simpler problem, perhaps? Yes? Let me do that. It's like, it's your own stupid fault. You're the one that wrote 10,378 to start with. That's true, I did that. It is all my fault. Let's do this example, though. What if we have n equals 375, all right, and I want to convert base 8 to base 8, okay? So to convert 375 to base 8, what you want to do is keep in mind what are powers of 8, right? So 8 to the 1 is 8, right? 8 to the 2 is what? 64. What's 8 cubed? $512, right? So the largest power of 8 that I can fit into 375 is 8 squared, right? So we start with that. Now, how many, so the question then is, so this is where we start. How many copies fit into 375, right? How about this? We can calculate 375 divided by 64, right? 375 divided by 64, what happens there? Let's calculate it. Let me show you how that goes. 375 divided by 64. See the stupid calculator, look at that. Isn't this is so helpful, isn't it? Look, 375 divided by 64 is, oh, it's 270, yeah, thanks. Thanks a lot. But if you hit this button over here on these calculators, it gives you the decimal, which then means something. So this is going to be 5, all right? And so if I do 5 times, so like this number, if I subtract 5 from it, that gives me that, and then that times, so the remainder is going to be 55 is my point here. So 5 times 64 is 320. So this gives me 55 as my remainder. So the point here is that 375 is equal to 5 times 64 plus 55. Okay, so this division tells me this equation over here, all right? And that's helpful because then I can work on this. So I've got 5 times 64, right, which is 5 times what? 5 times 8 squared, right? That's what I want. 55. What is 55? Well, what's 56? 56 is 7 times 8, right? So 55 we can rewrite as 48 plus what? Plus 7, right? You guys with me? And 48 is 5, so we got 5 times 8 squared plus 6 times 8, right? Plus 7. So your goal in converting to base 8 is to write your number as a sum of powers of 8. So I can fit 5 copies of 8 squared, 6 copies of 8, and then 1 copy of 7 like that. And so like in terms of base 8, 375 is actually equal to what? It's equal to 5, 6, 7, base 8. What's this number in binary? What's the number in binary if I add that on to this problem? Can you guys tell me? See, I can tell you the binary number. Here it is. Watch. 1, 0, 1, 1, 1, 0, 1, 1, 1, 2. There you go. That's the binary number. because I can use that trick, remember? That the octal, we can just replace each octal digit by its corresponding binary triple, like this. And that's the trick, yeah. So that's kind of fun. All right, let me go on here. So I hope I've done enough that you can get a sense of how you need to attack these problems. Basically, your goal is to find the biggest power of the base that you're looking that you can fit into the number. You subtract that off, and then just keep chipping away at what's left until you get it down to the ones digit. Should I work another? I probably should talk about primes, right? Because that's the other thing that I think is in your homework. If I have your homework. Let me glance here. Oh man, I grabbed the graph homework. That doesn't help us. Well, anyway, the homework is due much later, so if I've missed something, then I'll cover it next week, right? But hopefully I haven't. The other thing to talk about is prime numbers, right? So I hope you guys remember something about prime numbers from your elementary school, right? Do you? You guys remember what prime number is? What are prime numbers? So here's their definition that we can work with. Definition: n is prime if n is a positive integer whose only divisors are 1 and n. What do we mean by a divisor? If n is equal to ab, where a and b are positive integers, larger than 1, then n is composite. And we say A and B are divisors of n. So any natural number, like any whole number, we can break down into a product of prime powers, right? So like example 8. So you guys tell me if this number is prime or not. 11. Is this a prime number? It is, right? It's prime. How about this? 12. Is this prime? No. It's not, right? Because we can write 12 as 2 times 6, right? Is 6 prime? No, it's not prime. 6 is itself 2 times 3, right? So there 12 we can write as 2 squared times 3. All right, this is an example of the fundamental theorem of arithmetic. The fundamental theorem of arithmetic says that any number, any positive number, can be written as a product of primes or powers of primes, and uniquely so up to reordering. This has been known since the time of, Euclid. It's been known for a while. Let's look at another one. How about let's try 100. What's 100? 100 is what? We could write it as what? 4 times 25. So it's definitely composite, right? 25 is what? It's 5 squared, right? So 5 squared times 2 squared. So there's the prime power factorization of 100.